Okay, we are finally on air. Good evening or good afternoon, everybody. It's a pleasure for me to introduce today's speaker for the PRIMO talk series, who is Luca Ratti. I met Luca, we did the computation previously, something like 5, 6 years ago. Yes. And after this long circle, we ended up in being both members of PRIMO, which is nice. Luca did his PhD at the Polytechnical University of Milan in the group of Professor Quarteroni. Then he moved to Finland, to the University of Helsinki for a postdoc in the group of Samuli Siltanen. And now he's a postdoctoral researcher. He came back to Italy. He's a postdoctoral researcher at the University of Genova in the Malga group.
Yes.
I was right. Did I tell everything right?
Yes, yes. Everything was right. Yes, thank you.
So, Luca, please. The screen is yours, and have a good talk.
Thank you very much, Marco. And let me also thank the other organizers for this opportunity to speak here today. And thank you everyone for joining. So what I'm going to present today is this justified neural network approach for linear inverse problems, in particular for sparsity promotion regularization in linear inverse problems. And I will try to show an application in limited angle tomography. So let me first mention that the main contributions of this talk are in this reference here. By now there is a preprint on arXiv, but it's soon appearing on the Science Journal in Imaging Sciences. And I was working on this project when I was in Helsinki, and the team of collaborators is in a sense in between the University of Helsinki and University of Modena and Reggio Emilia. So from University of Helsinki, Tatiana Bubba, who is also a PRIMO member, and then professors Matti Lassas and Samuli Siltanen. And in Modena, Mathilde Garnier, who is defending her PhD thesis tomorrow, so it's very close to be PhD too, and Professor Marco Prato. So I thought it can be a good idea to start with a little bit of motivation. So speaking about the application we have in mind, and that was, in a sense, motivating our work in this direction, even though you will see that the topic will be very soon very theoretical, but let's start with a bit of motivation and application. So limited angle computed tomography. You may probably all know what is the radon transform, but very, very quickly for the ones who don't know computed tomography or radon transform, in a sense, the inverse problems we are interested in is to recover an unknown function u. You may imagine some properties or like a picture that you want to recover. It's typically an absorption coefficient without knowing u itself, but knowing the integral of u along all these blue lines that depend, of course, on the coordinate s and on the angle omega. So you suppose you have like think about an X-ray source here, and this X-ray going through the object, and you have a detector in the end, and you measure this kind of line integral, so an attenuation of the X-rays, and you let the detector turn around your object. And so you have, let's say, views from all the angles. And as I was saying, you want to recover the original image from the sinogram, that is this collection of the line integrals. Actually, this is an interesting problem, but it has been solved. I mean, it was solved almost when it was proposed in 1917. So the radon transform has this well-known inverse formula that is the filtered back projection, and was proposed again by Radon. But still, it's a very interesting problem, even though we have this formula to go from the sinogram to the image. It's very interesting because it's a very challenging problem in the sense that there is instability. So if you have some perturbations on your sinogram, you can screw up all the reconstruction, and you can get very large perturbations on your solution. So this is, in a sense, the meaning of instability. You know, small perturbations on your data, on your sinogram, imply large perturbations on the image. And this gets worse and worse when your data, your scenogram is, let's say, scarcely sampled. It means that you have just few views, for example, sparse angles, so just few angles from which you take your images, from which you use your X-rays, or you have limited angles, meaning that you probably have an aperture of your machine and you can't take from all the angles. And this is precisely what we are interested in. So limited angle tomography means that, suppose here I replace omega with theta, so indicating the angle that you are viewing. Suppose that your scenogram is available just not in the full angles, but just from this minus gamma to gamma. And you denote by this letter the radon transform limited to those angle and to those wedges, it's called. So what theory says is that in this case, uniqueness is preserved, actually, when you speak about infinitely many angles. So in the continuous case, as long as you have infinitely many angles, it doesn't matter if you have some missing wedges. But the problem is stability, even in the continuous setting. So in the discrete setting, you can imagine it can be a big problem. But even in the continuous setting, stability gets worse when you have this limited angle scenario. And what you typically see if you use the filtered back projection formula is that these streaking artifacts appear. So let me show you. Here is what happens if you do filtered back projection when you have all the data or the angles. But if you have some missing angles, what you see is these artifacts appearing. So it's like the discontinuities that are present in the image are running along these lines. Now you see are stretched along the lines. And these lines are indicating the missing wedge. So here you see with 60 angles, 60 degrees, 45 degrees, what you see is that the reconstruction gets worse, extremely worse, or even with very low angles. You get something that is basically rubbish. You cannot call this a reconstruction, of course. And there is a theoretical explanation that implies a little bit of microlocal analysis. So when you have some missing angles, it means that you're missing some parts of the wavefront set of the singularities. And this is a microlocal concept, but in a sense, I'm trying to recover it in the end, or half of the talk. Let's see. And as I was saying, this is in a sense a motivation because limited angle tomography is present in a lot of applications where you have, like, for example, in breast imaging, you have the machinery that is limited. So it cannot turn on all the possible angles. And so you're forced to have a limited angle computed tomography. Or in some other cases, you may have something like this. So in luggage control, what you can have is that maybe for time, or even in this case, for some aperture limitation, you cannot acquire an image from all the possible angles around the object. Or this is a more complicated application, but it's like a project that they had in the University of Helsinki, where they reprogrammed this kind of machine for dental imaging so that it can acquire an image from more angles of a single tooth, but it's still limited angles. So it's quite common in practice to have this problem, and you want to find some way to reduce these streaking artifacts. So I hope this is enough for a motivation. Let's move to unfortunately, a more theoretical discussion and a bit technical. So I tried to focus in the beginning on what are the key ingredients, and then to provide more details after that. So basically, the key ingredients are these four. We start with an inverse problem, and it's quite a simple inverse problem, we can say. So it's a linear inverse problem, and we suppose to have this linear map from two Hilbert spaces, and we want to recover the exact solution U, knowing these noisy measurements. It means that we have we don't have access to the image of the true solution, but we have this noise on it. But we have a bound on the noise. And what is typically done, especially if A is stable, as we saw before, is to introduce some regularization. And a good choice, I mean, not a good choice, a choice of regularization is to introduce this kind of sparsity promoting regularization. As you all know, a regularization strategy is good if it reflects some a priori knowledge that you have on your solution and that you expect to have on your solution. So in a sense, it's a good idea to use this kind of L1 regularization term if you expect your solution to be sparse. What does it mean? It means to have few components different from zero, but in this case, we are not yet specifying what is the basis. So it has few components different from zero with respect to an orthogonal basis that we introduce in the space. So it doesn't mean that it has just few pixels different from zero. If you introduce a different basis, you want the function, the image that you are trying to detect to have a sparse representation with respect to that basis. And this is a way. So you penalize the L1 norm of the coefficients with respect to that basis representation. And we call the change of basis W because the next point is precisely that we choose this orthogonal basis as a wavelet basis. What does it mean? That we introduce this kind of multi-resolution analysis. For those of you who know wavelet, this is actually a quite general description of what a wavelet is, but you can imagine that your basis functions are characterized by a level, so this J, and then a shift. So in a sense, being sparse with respect to wavelet basis means that you have maybe just a finite scale resolution. So you don't have too much details after a certain finer scale. Okay, this is something that can still be considered as a sparse image in with respect to the wavelet basis. So this is the choice that we are going to do, and connecting all these elements, so sparsity promotion and wavelet basis, what we get is something that is going in the direction of neural networks. And let's see how. So the most standard, let's say, algorithm for sparse regularization is, of course, iterative soft thresholding algorithm. And in a sense, what you do in ISTA is something like this. You start from an initial guess, and then you do many iterations. And in each iteration, what you do is you take the previous iterate, you subtract the same iterate, but you apply this normal operator, A transpose A, represented in the wavelet basis, plus this bias term that comes from the data. And then you give everything to this soft thresholding operator that is it's here, but it's just acting on each component of your vector. So this is very well known. When you fix a maximum number of iterations, capital N, what you have is just a map that takes your measurements and gives you back a candidate solution of your inverse problem. But what is the idea here is that this structure, so actually, sorry, this structure here resembles a lot the structure of a recurrent neural network, where you have basically something like this. So you have a bias term, you have a linear operator or applied on the previous, not iterate, on the previous layer or on the output of the previous layer. And instead of having n iterations, you have n layers. And in each layer, you do something like this, linear operations, a fine operation, let's say, and then a nonlinear operation, what is called activation function, that acts component-wise. So this soft thresholding is not actually a ReLU function, so something that is super usual in machine learning, in neural network, but actually it's something not too different. So this is the first key idea, that the structure of ISTA resembles a lot the layers of a neural network, of a deep neural network, because you typically do a lot of iterations, so it means a lot of layers. Before going to the center of the talk, let me just point out that we have some technical assumptions. I don't want to focus too much, but of course, I need a limitation frame. So it works, all this machinery works, assuming these technical assumptions. So let me just quickly go through them. You need to have a strongly sparse solution. So actually, few components must be different from 0. You need to have an injective map. And moreover, you need to have the normal operator, A transpose A, we can call it normal operator, must be translation invariant. So a convolutional kernel operator will work, something like this. This is actually quite typical, and for example, the random transform, limited angle random transform will work perfectly in this frame. And moreover, you need to assume that this kernel is, in a sense, smooth away from the diagonal. The diagonal is when the two entries are equal, and decays sufficiently fast when you go away from the diagonal. So these are technical assumptions. This requirement is that this is a Calderon-Zygmunt operator, or in a sense, a pseudo-differential operator. So it's related to the fact that then the network is called pseudonet. In a sense, this is here in this assumption. And on the wavelet basis, you actually require just the first order vanishing moments. So basically nothing, even the hard wavelet will work in this scenario. Okay, so let's start with the core of the talk. And I'm going to be a bit faster probably now. So how to give a convolutional neural network interpretation to ISTA? This is the point, because as I was saying before, when you have a neural network with n layers of this kind, this is a generic recursive neural network, you can imagine, okay, now let's fix this bias term to be as the bias terms that we have in ISTA. This is important, we have to fix it. We cannot learn it because it's where the data come into the network, data M. But then let's think about this linear operator. You can imagine some matrices as parameters that we want to learn. Okay, so what we can collect all the parameters in this mega parameter theta. And for every theta, we have a map that is a network. It's precisely a neural network that takes some data and gives you back a candidate solution. So there is a choice of this parameter, theta 0. So where instead of a generic operator, you put precisely the operators that appear in ISTA. For this choice of parameter, you exactly replicate n iterations of ISTA. So the neural network with this parameter is precisely ISTA. This is nothing new. This was already well known starting from 2010 and so on, from this paper of Gregor and LeCun. What is our idea is, can we say something more about this operator? Not just it's a linear operator, so we store like a huge matrix and we try to learn a huge matrix. Can we say something more using the structure of the operator A transpose A that we have in mind? Yes, and here comes the technical part. So suppose, define this huge matrix K as the matrix that represents the operator, the normal operator in the wavelet basis. Then you can represent this matrix in a different way, not just as a huge matrix, but first of all, you can separate it in blocks because the wavelet basis is decomposed in subbands. And then there is a more clever way to represent each block. The problem is that it's complicated, so it's very hard to explain in talks. I tried already 2 or 3 times. It's very hard to convey this message, but it's just a complicated formula. And you know, when it's complicated formula, it's typically also easy to prove because all the complication is inside the formula. So it's just a way to represent how a block of this block matrix acts on a part of the wavelet components. And it works like this, using discrete convolutions with some filters, and I have to describe who these filters are. And then you apply these operators here that are, sorry, it's not written here, sorry, that are downsampling and upsampling. I'm going to show you in a picture how it works. And then I'm going back to this definition of the filters. So I have to tell you how to define these filters here. But let's say instead of applying a huge matrix on your wavelet decomposition, what you can do is simply like this. You have a wavelet decomposition. You separate each subbands in the components. And then for each subband, what you do is some kind of convolutions with some kind of filters. But in order to do this and to have the correct size, you need to do some upsampling and downsampling. And then I have a more precise slide on this step here. But let's just say, after you do this kind of convolutions, you get a new wavelet decomposition. You sum them together and you get the result. So in the end, going from this part here to this element here in the end is like applying an operator A transpose A in the wavelet basis. But you can do it instead of using a huge matrix, using this kind of machinery. And just to say, the complication of the central step is something like this. So you have, if it's small, if it's a small scale, you have to first do convolution and then downsample, or just convolution, or upsample and then convolution. It's a bit technical, but what I want to say is that instead of applying a huge matrix, you can save a lot of parameters by using more structure. And in particular, of course, it's a complicated structure, but you can prescribe it to your network because these kind of operations are very natural in convolutional neural networks. It's just that typically you don't know how to create your architecture and you have some very fancy ideas on how to create the architecture. Here, instead, the architecture is complicated, but prescribed by the theory, by the intuition on how the operator should work. I hope it's clear. And here is instead is a slide on how to create the famous filters that must be put here. So the filters here can be created theoretically, computing those kind of integrals here, or you can create it in some clever way by just using the operator A transpose A and the wavelet transform. So what you can do is to create like a picture like this, activate a single pixel, and then apply your operator W star, A transpose A, and W, and get all these pictures here. These are going to be, say, 10 of your filters. You are going to need in this picture here 100 filters to create this strange operator. And you can do that by activating the center of each of these subbands. Okay, the message, let me, just go back to this. The message is you can have a different way of representing this operator, supposing that you're working in a wavelet basis and you have a convolutional operator. Okay, let me just skip this. You can use just smaller filters. That's a bit technical. If you, in a sense, if the information of your convolutional kernel is concentrated close to the center, so close to the diagonal, you can have a threshold on your filter, convolutional filters, meaning that you use just the center. And in this way, you use even less parameters. You have even less parameters to learn in your network. But I don't want to give any detail on this. Let me just now introduce finally our network architecture. We call it Pseudonet, and pseudo stands for pseudo differential operator. Let me show you why. So the network is precisely as I was showing before, but now this operator here, it's hard to write it, to say it clearly in a short presentation, but here, this operator here is not a matrix applied to the vector, but it's encoded particularly in this architecture that I was showing before. So applying this operator means that you split these into the subbands, you do the upsampling, convolution, downsampling, you collect them together. It's still a linear operator, so you can represent it like this. And what it means is that you do the operations I was showing before. And you can imagine that the central part of the filters that I was showing before is learned. So you want to learn a correction, a modification of the central part of the filters. And for simplicity, you fix the external part. I mean, you can compute it beforehand, you fix it, and you just learn a smaller number of parameters, so the center, but it's where all the information is concentrated. And what is the interpretation? The interpretation is that by linearity, what you can imagine is that you are adding another operator in the center of your filters. So you are correcting the normal operator, you are correcting the ISTA iterations by adding to this normal operator another operator that has a kernel K1 that is concentrated in the center, or on the diagonal, how it's called. So in the center of the filters. And an operator that has all the information concentrated in the diagonal is typically a pseudo-differential operator. So this justifies the name. It comes from microlocal analysis. I have a couple of slides later on, but I'm not sure if I will show you. But pseudo-differential operator comes from the fact that all the informations about the operation, the operator that you're learning, are concentrated in the central parts of the convolutional filters. And actually, we propose two possible implementations of Pseudonet. The first one is the filter-based Pseudonet, and it's precisely what I was trying to describe you just a minute ago. So what you do in Pseudonet F is that at each iterations, okay, there are some learned parameters, but then basically what you do is to apply this operator that is not learned and this operator that is learned. This operator is just the convolution and everything with the external frame of the filters that you can pre-compute. And this one is instead the convolution with the central part. And you imagine that the central part is made of learnable parameters. So then when you have this network architecture, you have these parameters that can be learned, and then you use your Adam or stochastic gradient to learn those parameters. But there is actually a more clever idea. Again, by linearity, it's not important to split the operator A transpose A in these two parts. You can just use the full operator A transpose A here, and then plus an operator that is concentrated only on the center. And this is the basic idea of Pseudonet operator based. So what you do is to just do a normal ISTA iteration, plus here you apply this operator here, and this operator, as before, is just a short way to indicate an operator where you have to split these in subbands and do convolution and so on and so forth. And the parameters here are just in the center of the filters. And it's called operator based because you can implement this step using any kind of method that you have on your operator. So for example, if you have a matrix free way to implement this operator, it's going to be super fast. Okay, so this is more efficient, and still you have few parameters. No, you have a lot of parameters actually, but less than learning the full operator in each ISTA iteration. So how is it the time? Okay, so I have time actually for a couple of very quick theoretical results before showing the numerical results. I think that one of the most— I think
you have 10 minutes, Luca.
10 minutes, so it's 5 and 5.
We started at 10 past 5, so
that's perfect. Let's do
only 25 minutes, so 10 minutes should be good.
Perfect. So half and a half. So let me just say the advantage of this kind of structure that is in a sense theoretically justified or theoretically deduced is that you have some theoretical guarantees. And the key idea is precisely this one. You know that there exists a specific choice of parameter, theta 0, that precisely replicates ISTA. So in a sense, your network can learn ISTA, the normal ISTA, or something different, but it can perform only better or equal to ISTA. This is the key idea. So in a sense, whatever results you have on ISTA, the standard one in the deterministic set, you can use it also here to study the convergence properties, for example, of this algorithm. So I don't want to get into any detail, but suppose that you are able to show that if your noise reduces, you have some kind of convergence of the ISTA iterations to the solution of the inverse problem. Then since our network, at least the optimal network, so the optimal choice of the parameter is going to perform better than ISTA, because of course it can learn also ISTA. So if it learns something different, it's going to be better. Then you have a convergence result also for this kind of reconstruction algorithm, even though if it's data-driven, but it's working better than a variational algorithm for which you have some theoretical guarantees. Let me just skip this detail and just give you an idea of why even Pseudonet can work even better than ISTA. Because of course it can be also equal to ISTA, but why can we learn something better than ISTA? The idea is that of course we can reduce in a sense some numerical errors due to the discrete representation, of course. We can also have a slight change of basis, so maybe we encode better the sparsity assumption. But what we realized actually in the revision phase of this paper is that this kind of reconstruction algorithm introduced what we call a micro-local regularization. Let me just give you just few details. I don't know how many people in the audience are familiar or are happy to hear something about micro-local analysis, but just a few ideas. So you can imagine, suppose that you don't learn a different operator at each iteration, but you just learn the same one. So you reduce drastically the number of parameters. But even if you learn just the same operator at each iteration, what you can see is that this modified ISTA with this lambda operator here can be seen actually as a standard ISTA for a modified problem. And the modified problem is this one. So in a sense, you are doing, this is something similar to what you do with the pseudo inverse, no? You have, with the Tikhonov regularization, sorry. So a variational regularization, you would put something like identity here. What happens if you put a pseudo differential operator as we are doing here? The idea is that the inverse of this operator now can be represented using Neumann series as something like this. So a sum of operators here plus a regular remainder. But this sum of operators is very nice because you see this, it's like applying sequentially this operator A transpose A lambda to the -1. And let me just give you an intuition of why applying this operator can be good for your problem. Because suppose that lambda is an invertible elliptic pseudo-differential operator, but just think about an elliptic operator. So the inverse of the elliptic operator is typically a regularizing, a smoothing operator. So when you apply this operator, A transpose A lambda to the -1, instead of A transpose A, what you get is that you can smooth out a bit the singularities appearing that maybe your normal operator introduces in the reconstruction. So this can happen if this operator is a pseudo-differential operator, but it's even worse when you have a more nasty kind of operator. This kind of Fourier integral operator is an operator that can move the singularities of the objects along some lines. You remember the streaking artifacts that we were seeing in the beginning. This is because the singularities of the image are moved along lines. So what this can do is actually not to prevent these singularities to move, but to reduce the intensity of the singularities. So in a sense, this is a kind of regularization, and we called it a micro-local, a regularization in a micro-local sense. So sorry for this complication. Let me just show you the final experiments and then we're done. So numerical experiments, as I was saying in the beginning, then we are closing the circle and we're going back to computed tomography. Computed tomography is a good application of this project because the operator is convolutional. The normal operator, R transpose R, is convolutional, and this is, for example, the kernel. There are some singularities. Actually, this is a bit more nasty than a Fourier integral operator, but still it can work even in this context. So we tried to implement it on some generated data and something more close to real data, just going in the direction of working on real data. We implemented it. Let me just show you. Yes, we were working on two kind of data sets. These ellipses data set, so images created with some ellipses, and we generate the xenograms, add some noise, and try to learn the best parameters. And you see this is the training set. Or the other idea is to apply it on something that comes from real data, but actually we had to manipulate them a bit because we cannot work with these large pictures by now. So we had to manipulate it, and so it's not actually real data, but it's these slices of apples coming from these projects where they try to see if there are some defects inside. So just for the machine learning people, we use TensorFlow. Actually, we have now also a version in PyTorch, and these are the details, but let me just show you the pictures. So what we do is, this is the target image we want to reconstruct. If you apply just filtered back projection, you see the streaking artifacts appearing, and they're not going away actually with ISTA, even though the numbers get a bit better, but the picture doesn't look like a good reconstruction. And then these are the two implementations of Pseudonet, actually just to show that basically they give almost the same kind of results, but the operator base is way more efficient. So this is it, and this is in the Apple case. What you see is, again, filtered back projection doesn't work. Here we have a wedge that is a missing wedge of 60 angles, so 30 plus 30, yes. And ISTA gets a bit better, but then our network performs better, at least with looking at the numbers. So I guess I was quite long. So let me just say, okay, conclusion, it's not so important. That's just, I was just trying to show that it's quite a fortunate paradigm for data-driven inversion. So we managed to bring a bit this traditional algorithm like ISTA closer to network architecture, and it's giving a lot of benefits, both in terms of interpretability and theoretical results. And open problems, future directions are actually working on this generalization problem is very interesting, because the convergence result that I was not showing but mentioning before works on the optimal network. But what happens if you have just a sample and you want to create a network, the best network according to that sample? Is it generalizable? So does it work independently of your sample, or does it converge with what rate? And this is actually very interesting. And I'm currently working on this topic actually on a different project in University of Genova. And then, of course, it would be very interesting to reach this complexity of real data. But by now, there is a bit of an efficiency bottleneck that we have to solve. But then we would be ready to apply our network also on bigger images and maybe with less angles. And of course, to extend it outside computed tomography, because as I was saying for most of the time, this works for a general operator A, satisfying the assumptions in the beginning. So for example, these are some examples. Thank you for your attention, and sorry if it was a bit longer, or yeah, almost. No. Thank you very much.
Thanks a lot, Luca. It was a very interesting talk, and don't worry, you were perfectly on time. 35 minutes flawless. So we're clapping on the I have this nice screen of all the pictures, but I can't see questions yet. So please, if you have any question for Luca, raise your hand or write a comment in the chat. Unmute yourself. Okay. I don't see anyone, so I can start maybe.
Yes, sure.
And so I have, first one is a curiosity. I think both of them are curiosities. So the first one is more, I work in optimization. So the first one is on the optimization side of the problem. Yes. The second one is on the deep learning side of the problem. Yes. On the optimization side, just to be aware of how things can work. So I've seen that you use TensorFlow and used Adam as a yes. training algorithm.
Yes.
Have you tried different algorithms? I expect that the choice of the algorithm used to train the neural network may lead to a better or yet a different network trained, which could give you results which can still be which can be better with respect to the one, or maybe eliminate some other artifacts you may have in your limited angle tomography. Have you explored other optimization strategies?
Well, actually, I have to say, we tried a bit, yes, but that was not like the main focus of our numerical experiments, especially because in the beginning it was so heavy. So you can imagine our main goal in the implementation was to try to reduce the number of parameters that we want to learn, because otherwise it was taking really a lot of time to train everything. So since it was very demanding, we haven't explored that much different kind of optimizers. Plus, I also have to admit that most of these numerical implementation was done by Mathilde, so I'm not really sure of all the tries that that we had. But what was important, yes, as you said, it's quite complicated to understand what is the effect of a different optimizer on the solution that you get, especially because you can really have, since you have a lot of parameters, you probably have some risk of overfitting, no? So it's also possible that even if you get slightly or not even slightly different parameters, then the final network still performs quite well. So you get quite different networks, but the performance is still comparable. Yes. This is probably something probably was there in this. Yes, I probably removed it from these bullets here, but one of the following bullets was to investigate different algorithms here. Yes, so thank you for the question.
And if there are no other questions, at least for the moment, from the other participants, I have another curiosity. So you showed us two tests, one on the synthetics data, one on the apples.
Yes.
So as far as I understood, but they were different tests. So you train the network yes. on the ellipses and test it on the ellipses, and then you perform another training test on the apples, and you test it on the apples.
Yes.
I was wondering, is there a chance you can do transfer learning in some sense in this kind of application? So you have, or the network you're going to train, it's specifically suited to a shape, or let's say qualities of the images, which I can imagine that in the case of the apples and in the case of the ellipses, they are pretty different images in terms of what you can have in the wavelet transform. So have you got any hints in this sense?
That's a very, very, very good question, actually, because the advantage of this kind of network that is inspired by theory is that in principle, it should be easier to generalize, because of course, ISTA, for example, doesn't depend on what kind of image you give it. No, of course, that's the plus of variational algorithms that they generalize very easily. So we don't have yet an answer on this. So we haven't tried this cross. But in principle, in very super principle, yes, it should be easier to generalize. So the network can more easily generalize from one sample to another. The point is that precisely as you were mentioning, and this is, you were already giving the answer probably to your same curiosity, is that you don't have the control on what kind of features your network learns about the sample. So you don't really know if the correction that your network learns is best suited for those kind of images, maybe the ellipses or the apples, that has some peculiarities. So as you were saying, maybe some scales, some details at different scales. So the ellipses, for example, don't have very small details, but the apples do. So probably if you train on these, probably the network learns that you don't have to correct too much, maybe on the finest scale. So on some of the filters will not be so important. And if you then try to apply here, you have a problem. So that's the point. And that's probably, that will be seen that probably in the theoretical results on generalization, they will be very far from then this kind of application. So you maybe have some generalization results, but supposing that you have an enormous sample, that's possible. But at least the idea is that this should be closer to variational algorithms that in a sense generalize better. So we have this hope, yes. Okay, thank you. Thank you for the question.
I'm done with my question, I promise.
Maybe I have one, if there is still time.
Yes.
Okay, thank you, Luca, for your nice talk. Maybe I lost it. N for you is the number of layers, which is the same of the number of iteration that you perform with ISTA. Is it right?
Yes, exactly.
And how do you choose it? I mean, how do you? Because I think that this could be a limitation, but how the solution changes if you change N?
That's a very good question. So by now we consider N as an hyperparameter. So we fix it around 100 or probably 120, something like that. But the idea is that, of course, 100 iterations are not too much for ISTA. Maybe it requires 1,000 iterations or something like that. But hopefully it's faster than ISTA in converging. So it makes sense to have this number. We tried also with different N's, but actually that's a specific task in neural network, that is hyperparameter optimization. And that's going to be very demanding, I guess. What we were considering is exactly this problem. So try to see what happens when we change N, and also coupled with this, in a sense, try to see what happens if we fix the operator for some iterations. So maybe we have more iterations N, but say you keep the same operator, you don't learn a different operator at each iteration, but you learn it, I don't know, once every 3, 5, or 10 iterations. So that could allow to have more iterations, even without having an exploding number of parameters. And that's what we tried, actually. I was extremely fast here, but the final implementation is, yes, we have 120 iterations, but we fix the parameters over 3 consecutive blocks. So this was our final decision. So yes, I hope it answers about.
Yeah, because I was thinking, how about to reduce N and maybe to increase the number of epochs?
Yes.
I don't know. This maybe can be an idea. I don't know. But I'm not sure what I'm saying. So
no, I mean, that's an idea. Of course, the problem here with these kind of numerical experiments is that you cannot experiment too much. Let's say I'm more happy when I have to. I mean, of course, also in PDEs, as Marco knows. I mean, when you have a very large system, maybe it takes days to simulate, and so doing an experiment can.
And you have a finite lifespan.
Exactly. So here in machine learning, maybe you say, let's do this kind of experiment. And then 2 weeks after you have the outcome. So it's not super easy to try everything. But
now that you mention it, what is the training time in this case? Just for curiosity, how much did it take to TensorFlow to?
By now, I guess on these 128, it's about a few days. Yes. Not on the
few
apples.
Days
no, yes, also on the apples.
Okay. I see.
But yes, that's the bottleneck I was mentioning.
Okay. I see there is a question from Daniela Di Serafino. And Daniela, if you want to ask your question, unmute yourself.
Thank you. I don't know if you can hear me.
Yes.
No, I muted. My connection is very, very bad. So I'm afraid I don't show up for this reason. Just a suggestion from my point of view. It would be interesting to fix the time and to see what happens. I try to explain better. I don't know if I missed something, in the sense that instead of fixing the number of iterate, in my opinion, hides some things, because epochs means that you make a full pass through something. I don't want to go into the details. It would be very interesting to fix the time and to see what happens if I fix the time I want to run my training and what I get by using ISTA, and to see how sensitive all this procedure is to time. Because now there is a big effort to not waste energy, to not waste time, etc. So at least, just like a suggestion, maybe you did it and I missed something. Yes, but if you try to fix the time and you decide how long you want to wait for the result, it might be interesting to know if you are able to reconstruct the image to get the parameters the way you want, etc., etc. Just an idea. I don't know if you try to do that. And usually I'm curious about that, because I want to know how long I must wait to get something that I consider reasonable from the point of view of the results of the reconstruction of the image. Just a suggestion. Maybe you did it.
No, actually, we haven't done it. And thank you for
Can you still hear me?
Yes, I heard, and thank you very much for the suggestion. We haven't tried it, and I actually know very little about it.
No, of course, this changes the perspective, because in my limited experience on that, everybody tends to fix the iterations or the number of epochs, etc. But often you want to take into account also time, in the sense that in the end you want to have a good and fast results which is suitable for your final goal. But it's just a suggestion, no more.
And also, yes, that's true. And also we know, I mean, I know very little about this, but we know that sometimes convergence, when in cases of semi-convergence or something like that, it's not always useful to wait until the algorithms has done a lot of iterations. So maybe an early stopping or something like that can help. Thank you for the suggestion.
No, okay, thank you for accepting them. And okay.
Okay.
Yeah, I deactivated my microphone to not disturb. So I don't know if there are any other talks, but I see it's 6 p.m. People in the parking lot will confiscate my car if I don't go to take it back. So yeah, it's risky for me to stay longer, but in general, I think that an hour is gone, and we can stop here. And of course, I think that we will put the slides on the website, the video on YouTube, and I think that everyone who is curious can contact you. Maybe they have your website on the PRIMO website, so they can find you easily.
Yes, of course.
Perfect. Thanks a lot, Luca, and thanks to everybody for attending this nice seminar, and see you in a couple of weeks.